Hello everyone and welcome to our today's webinar. It will be about our laser flash analyzer. Before we start with the actual webinar, maybe some further participants may join. Here's some organizational information. So all of you are muted. There will be a moderated question answer session at the end of the presentation. And if you have any questions, comments, please use the chat or the question and answer tool, and I will answer all of your questions then after the webinar. Of course, if any further appear, just give us some feedback after the webinar and contact us. The webinar will be recorded. You can find the recording then shortly after the webinar in the chat, where you can download that, and if you like to have a look again onto the presentation. I also want to introduce myself. So my name is Erika Hahn. I'm working for Linseis in the application lab, and I'm responsible here for thermal conductivity and thermoelectrics measurements. For those who do not know the company Linseis Messgeräte, also a very brief introduction. So the company was founded in 1957 by Dr. Maximilian Linseis, whom you see here on the left picture. And now the company is in third generation led. So first of all, Klaus Linseis, the son of Maximilian Linseis, was the CEO of the company, and now the daily business is managed by two of his sons, Dr. Vincent Linseis and Florian Linseis. The main business field of Linseis is the production and the development of instruments for thermal analysis, also for thermal conductivity and thermoelectric materials, so basically material research. In addition to that, we also have some own service laboratories where we can offer some service measurements on a few samples. The headquarters of the company is in Selb, which is in northern Bavaria of Germany. And additionally, we have own sales and service locations in the US, China, and India, and also more than 65 distributors worldwide who help us to trade our instruments. An overview over the product range you can see here on this slide. So starting from classical thermal analysis with calorimeters, thermobalances and SDAs, as well as dialutometers for thermal expansion measurements. We have also instruments for thermomechanical analysis and a broad range for thermal conductivity and thermal diffusivity tests, where the LFA also belongs to. In addition to that, we have instruments for the characterization of thermoelectric materials, as well as the Hall effect, and both and also the thermal conductivity can be also analyzed for thin films in a micrometer and nanometer range. The unique part here about Linseis is the high level of options and customizations which are possible. For example, we can have an evolved gas analysis or high pressure instruments and instruments for a very high temperature range. That was the introduction about the company. So now we move more into our today's topic, the laser flash, which is an instrument for the determination of thermal diffusivity or thermal conductivity. But first of all, we should quickly talk about heat transfer in general. Basically, there are three mechanisms where heat can be transferred: radiation, which is the emission of electromagnetic waves, and all materials radiate thermal energy. There's also convection, which is a particle stream, and heated liquids, which carry here the thermal energy. For example, a heater or the Gulf Stream. And topic for today will be the heat conduction, so characterized by thermal conductivity, where no transportive material is happening and the heat is transferred either via phonon contributions or lattice vibrations or by electronic contribution due to freely moving charge carriers, or by a combination of both. One can classify here a little bit some materials. For example, insulators. Here the heat transfer is dominated by phonon contribution. In metals, the electron contribution is dominating heat transfer. Well, we also have this very useful law called Wiedemann-Franz law, which is relating the thermal conductivity to the electrical conductivity, where both of them are connected via the so-called Lorentz factor L and the temperature. For semimetals and semiconductors, both parts, so phonon and electronic contribution, transfer the heat. And here one can see that there is a strong temperature dependency, so that in one temperature range, maybe the phonon contribution is dominating, and at higher temperatures than, for example, the electronic one. A good picture to keep in mind what are the mechanisms of heat transfer is this one here, where we have the fire bit, which is sending out thermoelectric and thermomagnetic waves. So heating up the pot. Within the pot, there is a water filled in. Within the water, the heat is transferred by convection. And as also the pot is heated up, you will recognize that using then the handle here, where the heat is transferred via conduction. So of course, in some cases also more than just one heat transfer mechanism can happen, so that, for example, within the water, there's convection as well as thermal conduction, so that it is a combination of that, but the convection might dominate here more. The thermal conductivity range, which we will focus on then with the LFA, is a very broad range covering different materials. So you can see here on this table some examples for the thermal conductivity of different materials. You see here liquids have a rather low thermal conductivity, insulation materials even lower, and on the opposite side we have metals with high conductivities, and diamond has a extremely high conductivity of 2300 watt per meter Kelvin. And this is the challenging part, to be able to measure this very broad range of thermal conductivities, also in a broad temperature range. Within the presentation, I will also use the labels thermal diffusivity and thermal conductivity. Both of these properties are related to each other, but describe different mechanisms. So the thermal conductivity of a material is a measure of its ability to conduct heat, so thermal energy, whereas the thermal diffusivity is the measure of the ability of the material to conduct thermal energy relative to its ability to store thermal energy. More precisely described, the thermal diffusivity is a propagation of a temperature difference within a material, so how fast the temperature difference is leveled out. And the unit typically given is meters squared per second. The thermal conductivity describes the propagation of a heat difference in a material, so how good heat energy is conducted through a material. As mentioned, both properties are related to each other. This you can see here on the bottom of the slide, where the thermal conductivity is just a product of thermal diffusivity, specific heat capacity, and density. All of these properties are temperature dependent, so it is very important to test all of these properties in dependence on temperature. There's also, of course, the question why we need to know the thermal conductivity. The main answer here is thermal management. The thermal conductivity is a crucial parameter for the design of a device. So, for example, one can use a thermal paste to remove some heat from electronics, um, or one just wants to avoid overheating of parts or um, thermal stress within the material, which might lead to some cracks, as shown here on the bottom. In addition to that, the thermal conductivity can be also a parameter used for simulations, for example, for casting, solidification, or sintering processes, where it might be that the thermal conductivity of a material might depend on the thermal pretreatment. So here one needs to check the conductivity to find out a good way to treat the material. Last but not least, one can also use the thermal conductivity as a factor for quality control, where deviations in thermal conductivities might be a hint that there's some impurities within the material. In general, there are two methods or two classes of methods how to measure the thermal conductivity. We have the transient methods and the stationary methods. Within the transient methods, the sample is subjected by a thermal disturbance, and the disturbance is then observed as a function of time. To this method, also the laser flash belongs to. Advantages is, as we directly have a look onto the sample when bringing in a thermal disturbance, the measurement times are very short. In addition to that, the transient methods typically allow a broad thermal conductivity as well as broad temperature range. Disadvantages here is that the theory behind the evaluation is typically quite complicated, and what we will see later on, that the LFA firstly measures only the diffusivity. On the other side, we have also the stationary methods. Here, one needs to wait until there's a stable temperature gradient through the sample, and we have a stable heat flux going in as well as out of the sample. And to these methods belong, for example, the guarded hot plate, the TIM tester, or the heat flow meter methods. And disadvantages here is that as we have to wait for a stable state, measurements take quite long. And additionally, also the thermal conductivity range is quite limited, as well as the temperature range. Mostly these methods go up to maybe 100 or 500 degrees Celsius. But advantages is that this investigation delivers directly the thermal conductivity. The product range of Linseis for thermal conductivity measurements for, let's say, bulk materials is the following. We have the laser flash analyzer and the THB working based on the hot wire technique. These both are transient measurement methods, and on the right side we have our stationary methods, the TIM tester and the heat flow meter, with which both work according to the hot plate setup. Now we have a much more closer look onto the laser flash analyzer, how the method works, what samples can be investigated, and which news we have for our laser flash system. We're starting from scratch, so the laser flash analyzer is a standardized method according to this ASTM norm for the measurement of thermal diffusivity, and this norm describes that a small, thin disk specimen is subjected to a high-intensity short-duration radiant energy pulse. The energy of the pulse is absorbed on the front surface of the sample, and the resulting temperature rise at the rough surface is recorded, where we use here an infrared detector to record the temperature rise with time. A typical signal looks like that. Now you first have the baseline, then at time stamp 0, the laser shot or the light shot will be initiated, and then we have a look onto the temperature rise with time. Out of this curve, one can then calculate using some physical mathematical models the thermal diffusivity according to that formula, where we have the thermal diffusivity is the product of a constant factor and using the sample thickness squared divided by the so-called half-time rise, which can be here seen how it is determined. So we determine first the maximum amplitude and divide it by 1/2, and then have here the timestamp of the half-time rise. This working principle is realized the following in our system. So we have on the bottom our power source where the beam is directed then to the sample, which is located here and is surrounded by a furnace. And on the top, we have then the detector. As mentioned before, we have a high level of options and customizations possible. Here are some examples of what we can do. So starting from the bottom, we have two different power sources, either a xenon lamp or a laser source, where the xenon lamp has a little bit less energy available per pulse. For the sample, we have also several options. So we have here a sample robot, either for typically 3 or 6 samples, depending on the type of instrument. One can also have just one sample or up to 18 samples within one system. For the sample robot, there are different sample holders, which I will show you later on. And these sample holders cover a sample dimension range from 3 to 1 inch diameter. For the furnace, we also have a lot of different possibilities, which of course depend a little bit on the model type, so that not all combinations here are possible. So we have furnaces for the low temperature range, then for moderate up to 1500 degrees Celsius temperature range, and then for even higher temperatures. So for temperatures higher than 2000 degrees Celsius, going up to 2800 degrees Celsius. In our product range, we classified our instruments the following. So we have an LFA 500 series, which all have the xenon lamp as a power source. We have the possibility to have a variable pulse length so that one can adapt the energy of the pulse towards the sample. One can choose to a 3 or 6 sample robot. In a special version, there's also a 5 sample carrier available. There's the option of the PLH add-on for films, which I will present later on, and these furnaces can be equipped to the system. There's also the LFA 1000 series, which all use a laser for the power source, which has, as mentioned before, much more energy available, where we have also the possibility to tailor the pulse energy or pulse length to the sample so that one have an extended measurement range of various materials. The furnace program you can also see here. So we have also many possibilities to cover different ranges. And the last series is the so-called LFA 2000 series, labeling all instruments which measure up to 2000 or 2800 degrees Celsius. Here you can already see that here the sample throughput is a little bit more limited. One can either measure 1 or 3 samples at the same time. What can be measured here as well with the high temperature series is that we also have tungsten furnaces available or graphite furnaces to cover different applications. All of these models typically measure in vacuum. The high temperature versions typically measure in helium or argon. However, all of these instruments have the possibility to perform measurements in vacuum or in different gas atmospheres with a complete temperature range each. Um, as mentioned before, we also have this high level of options and customizations. Here are some examples for some, let's say, more special setups. One you can see here, we have an LFA 1000 setup with two furnaces. So one low temperature furnace and a high temperature furnace to cover the most extensive temperature range, where one have here where one has these two furnaces on the tabletop, allowing to switch through different temperature ranges. A broad application range is nuclear applications or application measurements within the glove box, for example. Here we have different possibilities to separate the electronics and or the laser from the main unit. Here you can see some examples. So here, for example, also using a laser fiber optic, we have decoupled here the laser from the unit. On the lower left, you can see a tungsten furnace, also for a glove box application up to 2400 degrees Celsius with the sample carrier here. And on the right, we have a glove box version where we had very limited space and had to redesign our complete new instrument. Um, And also the sample holder can be adapted to such glove box applications. Here we made sure that the sample holder can be handled also with a manipulator, so with a robot. In general, what might be also advantages for such application is that we offer different detectors, a Peltier-cooled one and a liquid nitrogen one. Peltier-cooled means that the detector is thermoelectrically cooled, so there is no need to have liquid nitrogen. In general, we typically recommend the liquid nitrogen cooled detector as it is the more stable and more precise one. Coming now to the different sample holders. So the basic idea of the laser flash is to measure solid materials with thicknesses ranging from zero point 0.1 to 6 millimeter, depending a little bit on the kind of material, which thicknesses can be measured. Our sample holders allow various sample sizes from typically diameter 10 millimeter to half an inch or 1 inch diameter. There are also some sample holders for square samples for 10 or 20 millimeter samples. But all of these sample holders are designed the same. So on the left, you can see here the carrier for the sample robot for 3 samples and for 6 samples. Within each position, one can place an individual sample holder, meaning that within one carousel, you can have up to 6 different sample holders with also different geometries inside. The sample holders itself are designed the following. So we have the carrier for the sample, and in addition to that, a lid for the case that here the borders are not closed completely and some light would directly penetrate to the detector. This we want to avoid, and because of that, we have here the lid. The equipped sample carrier is then placed into the instrument. Here you can see an open one. So here is the carrier for 3 samples. In the middle, we have the sample thermocouple measuring the sample temperature. It is very close to the sample and at the same height as the sample, so that here we have a precise measurement of sample temperature without the need to contact the sample. The thermocouple here has a fixed position. We also close this sample holder as we want to guarantee a homogeneous temperature stabilization within the instrument, within the furnace, as well as within this sample carrier. Here you can see then a closed one, how it is placed in the system. The sample preparation for solid samples looks the following. So we have here in this image a disc-shaped sample. Both surfaces will be coated with a thin graphite layer. This be due to maximize the absorption of the energy by the xenon lamp or the laser pulse. This sample is then placed into the sample carrier. Here we made sure that we have as less contact as possible to the sample to avoid heat losses, and then we place the cap, and this can be then placed in the carousel. So, as just told, the basic idea of the laser flash is to measure solid samples, but that one can extend to further applications. And here you see on this slide some of our special sample holders. For example, we have sample holders for liquids, pastas, and powders, where we have a closed bottom and top. Important is here that the lid is fixed then to the bottom of the sample crucible. In the middle, we have a precisely defined thickness, which won't change during the temperature measurement as the lid is fixed. For the case that, for example, a liquid expands at higher temperatures, we have here some excess volume on the sides where the liquid can expand into it without spilling out of the sample holder. In addition to that, we have a specialized sample holder for liquids, powders, but this sample holder is especially designed for the melting of metals. Here we have the carrier. In the middle of that, there's a hole fixed for a sapphire crucible where the sample will be placed in. That will be fixed or closed with a lid. And then the lid of the carrier will be also fixed and screwed so that nothing can move at higher temperature. Meaning that here with these sample holders, one can also start with a solid sample and melt it at the higher temperatures. As mentioned, the sapphire crucible is especially suitable for metal melting to avoid too much contact with graphite, as all of our sample holders are mainly designed out of graphite. For foil samples or in-plane tests of thin materials, one can use this adapter here. We also have some containers for a pressure-dependent analysis. Typically, the laser flash method is a contactless method where we don't apply any pressure to the sample. But with this sample holder, one has the possibility using a torque wrench to define the pressure on the sample. For really very special application, the measurement of lamellas, we also have designed a sample holder. This sample holder is, for example, also used for in-plane measurements. So first one measures the bulk material with the classical sample holders, then cuts some slices out of the material, turns it by 90 degrees and places it into the sample holder for lamellas. So these are the sample holders for, let's say, more special applications or the widened application range of the classical laser flash idea. Yes, so as soon as the test is done, one also needs to evaluate the measurements. For that, there are several models available. These models are necessary as the experiment has non-ideal conditions, deviating from the ideal case, so from theory, and these non-ideal conditions are heat losses to the surrounding, to the sample holder, for example, and the so-called finite pulse length effects appearing for thinner and high conductive samples where the measurement time is very low and must be related to the time of the pulse. The pulse itself, so the xenon lamp pulse or the laser flash pulse, are in a range of a few or 1 millisecond, just for your information. So as mentioned, there are many models available. Modeling here this heat loss or the finite pulse length effect. Typically, most of the models just focus on one. The unique part about Linseis is that we have the combined model by Dr. Dusa, who combined both effects into one model, so simultaneously fitting um, both effects. And this is a, let's say, more or less universal model, which can be applied to very many samples. In addition to that, we also have a model for translucent samples or for samples consisting out of several layers, up to 2 or 3 layers. I have also told you before that an option for the detector, we have either a thermoelectrically cooled detector or a liquid nitrogen cooled detector. Here you can see the comparison of a measurement performed with both detectors at the exact same temperature using also the same material. What one can see is that the signal of the thermoelectrically cooled one is a little bit more noisy. However, it is still very stable and can be evaluated with a high precision. But as mentioned, in general, we typically recommend here this liquid nitrogen one as it is the more stable and the, let's say, a little bit more precise one. And as in research typical, a very precise measurement is the most important part. As a further option with which the system can be equipped with, I have mentioned the PLH option, and this I want to briefly explain to you right now. As I have told you, the laser flash is a system designed for the thermal diffusivity measurement of solid materials in the range of 0.1 to 6 millimeter. Even the 0.1 millimeter sometimes cannot be realized that well. The issue here is that the response of the sample is very fast and might be too fast for the length of the pulse. So the length of the pulse should not overlap with the reaction of the sample, and for very thin samples, this might happen. Because of that, we have developed this technique in the system called PLH, which stands for periodic laser heating, and this extends the range of possibilities within the system regarding thinner materials. This is especially a useful tool for the LFA 500 series with the xenon lamp, as the xenon lamp has, on the one hand, lower energies available, and on the other hand, typically has a quite fixed pulse length. For even lower thicknesses, we have other techniques available, like the thin film laser flash, but this is discussed more in detail in another webinar. Just as a rough introduction, this is how the periodic laser heating works. It has the same setup as the laser flash. So we have a laser, a sample, and on the opposite side, the infrared detector. The key difference is that we don't have this time framed pulse towards the sample, but we now have a modulated laser light, meaning that we are working here in the frequency domain. Because the laser light going into the sample is modulated, also the emitted infrared radiation will be modulated. This we collect and evaluate also using a lock-in amplifier. So we have in the end a look onto the phase shift and the change of the amplitude from the induced signal to the reflected signal of the sample. We evaluate it to have a linear relation, as linear relations are easy to evaluate. And in the end, we also get the thermal diffusivity out of the measurement. So that this PLH method is an extension for thin films, and both modes can be used in the same setup. Next part of the presentation will be the news of our laser flash system. The big news is that we have a new LFA version available from next year on, and here you already get a preview onto that. First of all, we changed the design of the instrument and also the design of the software, and this I will show in more details right now. So the changes we have done regarding the hardware is the new housing, going from the, let's say, more blue design to a more modern black design with a glass panel on the front with a touch display. We also have a completely new electronics, which allows a more stable operation as well as a fast data acquisition. And as mentioned before, this system can now be upgraded with this periodic laser heating technique so that two techniques can be used within the same setup, allowing a much broader range of applications. Regarding the software, the main change is summarized is on the first glance one can directly see we have a new graphic user interface, which allows a more intuitive operation. In addition to that, the operation is now data-based, so that the raw data is stored on a database, and you can combine these values with results of further measurements of Linseis instruments, like, for example, the dilatometer or the DSC, the calorimeter, and the results can be evaluated in one project, which helps, for example, an easier calculation of thermoconductivity so that we collect the diffusivity data with LFA, specific heat capacity with a DSC, and the density change with a dilatometer, and all can be then evaluated in just one project. The database operation also allows then the creation of different user accounts with user-dependent settings, meaning that if you have specific temperature stabilization criteria or further settings, this will be stored in your account and you don't have to change that every time when you open the software, especially suitable if the system is used by many different users. A further change within the software is that now a live tracking of the values independent with temperature is possible, where you can also recall already performed shots. This I will show them later on. With the new software version, we also tried to improve more the feedback to the user with more and also more clear error messages and warnings to help to simplify performing measurements. On the display, on the touch panel of the instrument itself, one can also check the progress of the measurement, and this helps to understand the time frame of a measurement. An important part is also that one can change the software between a default and an expert mode. So for example, for very experienced users, one have the possibility to also use the export mode, where one can have more specific temperature profiles or switch also off the automatic optimization, which the software does regarding detector settings or measurement time. For those who are not that familiar with the instrument or just don't want to define too many points, there's also the more simplified mode, which can be used in the instrument. So that is how the software interface looks like. So we have on the left the status of the system. One can also check what is the system doing, what is the temperature level at, is it heating, is it stabilizing, and so on. To initialize a measurement, one first needs to configure the sample carrier. One can choose here between the available sample holders. One defines the sample, defines the thickness of the sample. One can choose between the sample holders, directly place in here already heat capacity and density, either out of database information or out of a measurement file, or one can use just a fixed value here, which one types in. The next step would be to set up a heating profile. Here you can see the expert mode where you can define the temperature, the heating rate, the tolerance, stabilization pause, number of measurements, and the waiting time in between measurements. So a very extensive um, table here where you can have a lot of possibilities. For the default mode, you mainly just type in the temperature and the rest of the parameters will be within the settings as a default value placed in here. During the measurement, the software will look the following. So within the so-called single shot measurement window, one can perform manual tests, also do a manual heating up to a specific temperature, and as mentioned, perform manual measurements. However, mostly one uses the software in the automatic mode here with the automatic measurement, where the set temperature profile is done automatically. And here you can see how it will look like during a test. You can see here the individual shots taken at target temperature of 50 degrees Celsius, as we just have two temperature steps set up here. We have already finished 50% of the measurement, and we can see that the system is starting to heat up to the next temperature. Here in the single shot measurement, you can see the energy or the settings of the pulse source or the laser source. In addition to that, the measurement time, aperture, and amplifier. The latter both are for the detector, but all of the three properties on the top are optimized also by the software. We have not only the combined model included in our software, but many more. Here you could have the possibility to change between the models. As a default user, you can just use the combined model as it is a very universal one. And on the bottom, you will see then the diffusivity as well as the fit quality and the temperature of the sample recorded at a shot. This diagram here can be also enlarged, so you can zoom into this image. You can have a closer look onto signal, pulse, and the fit. You have the possibility to also hide one of these graphs. As soon as the measurement is finished, you will get information that the test is done. On the bottom, you see then here the graph of the recorded thermal diffusivity independence on temperature. You see both always in a diagram as well as in table, and all of these results can be exported as well. So here you can see then how this table looks like. So for the result, we have the nominal temperature, the temperature of the measurement, the recorded thermal diffusivity, the used model, and fit quality. If you have already put in some density and specific heat capacity information, also the conductivity would have been displayed here. A good part here is also that if you recognize that one of the chutes does not fit to the further ones, you can just double click on a line and you can see here on the top then the recorded curve where you can find out if maybe something did not work as it should. So that is the preview on our new software, how the structure will be done within the new version. So this is our big news here that we have the new version of the laser flash regarding design, hardware, or electronics in general, but as well also the software. To come to an end of the presentation, I just want to show you some applications of some measurements performed with the laser flash. A standard one is the measurement of graphite. So here a high temperature system was used where we measured the thermal diffusivity of graphite up to 2800 degrees Celsius with many temperature steps in between. So that is a very classical example on measurements. We also performed some measurements on refractories, so on typically ceramic-based materials, which are very stable at high temperatures. So here a test was performed of 3 materials up to 1200 degrees Celsius, and we can see a good difference between those materials. And this test is useful for simulations, for example, for thermal management. So on the one hand, we had now the graphite. Here we have, let's say, ceramic-based materials. The system can also measure metallic materials or, for example, polymers. Here we have an example for some steel alloys with 2 different degrees of alloying, and we can see here a significant difference of behavior of the both materials, just strengthening the point that the investigation of the material properties are very important to know how the materials behave, especially at higher temperatures, as this can be very different from material to material. Here's also a special application of a phase change material. So here we have an application of a molten salt. So at room temperature, the salt is solid, but gets liquid at higher temperatures. And here a test was performed from 773 Kelvin to 973 Kelvin, where the thermal diffusivity was measured. So the diffusivity was tested in the liquid state, where this special sample holder for liquids was used for the investigation. And here a second example of a liquid measurement. Here we tested a silicon oil up to 100 degrees Celsius and combined the data of thermal diffusivity with specific heat capacity measurements done by a DSC. In the end, we could calculate then the thermal conductivity. So that just illustrate a little bit the application range. To summarize, our laser flash systems are very universal tools for the characterization of thermal conductivity or thermal diffusivity of various materials ranging from solids to liquids, pastes, powders, phase change materials, or coatings using the multi-layer model. Some of the materials can range from insulating materials to very high conductive materials like diamond, covering also ceramics, polymers, and metals, or combinations out of that. Using our sample robots, we have a high sample throughput, and we have many possibilities of furnaces up to even 2800 degrees Celsius. With the powerful laser, we have up to 25 joules available per pulse. And for the evaluation, there is the combined model, which is a very universal model as it simultaneously models the heat loss effects as well as the finite pulse length effects. In addition to that, the LFA 500 series can be also equipped with the periodic laser heating option, so allowing an even broader application range from thin films to bulk materials within one instrument, and this combination is also patented. And the big news we have here is that we completely revised our laser flash instrument to a new design, new electronics, new software, which will be available beginning from next year. So at this point, I reached the end of my presentation. I want to thank you very much for your attention.